Welcome to a lesson with Dr. Powell. Let's take a look in this video at the arithmetic Mobius mu function, and we're going to look at it from a Poset perspective. So this is a divisor Poset, or divisor lattice, has factors of 60, and this is a Poset diagram. Now, in this description, we're going to be thinking about the arithmetic Mobius mu function as giving us the elements in the top row of a Mobius matrix associated with that Poset structure. So you can go to one of my other videos that talks about what a Mobius matrix is associated with the Poset structure, but we're going to go on from here and kind of see how that works. But the idea is, behind that, is if I have some kind of structure, like be a Poset diagram, and I were to put in like elements in here, just any kind, like 4, 5, 7, 10, say, or whatever, okay, associated with this structure, the Mobius matrix is like a function which gives out numbers that I could put in the exact same shape, or diagram, Poset diagram, but I'm going to change the vertices such that the following thing holds. All right, so whatever I put here, the sum of it and anything below it is going to match with that. So 10. Okay, this guy, whatever I put here, the sum of this and anything below it will match with that 4. So I better put a -6 here. 6 plus 4 is, -6 plus 10 is 4. And then here, what do I put here? I have to put a -3. Then I think, okay, what do I have to put here so the sum of this and anything below it is going to be equal to 5? Well, 10 minus 9 is 1, so I'm going to be adding on a 4 here, and that would complete it off. This Mobius matrix is going to be a function. We can think of it in terms of columns. So if we input the column 5, 7, 4, 10, it's going to output a column associated, like over here. It's going to give us 4, -3, -6, 10, where I've kind of ordered these the same way according to the shape, right? It's going to output that. So it goes from like sums to maybe like nodes or summands, if you will, or whatever, just things that add up to make these entries over here. And we could actually build this using like standard basis vectors or elements here. This is a linear transformation, homomorphism, however you want to think about that. But looking at standard basis elements, where they're going to head, we can do that to figure out what the columns are of this matrix. For instance, let's look at E4. What would that be? So E4 is kind of like, wait a minute, so the input's going to have a 1, and the rest are going to be zeros, right? So because you're going to be inputting the column 0, 0, 0, 1, and that's going to look like, in this case, that's going to look like we have 1, 0, 0, 0. Okay, and we're going to figure out what the solution would be for that over here, and you can check it. It's going to be as follows. It's going to be, let's see, we're going to have 1, -1, -1, 1 alternating, and that would give us that column. Okay, so we're interested, the function we're interested in is going to give us the top row of this matrix. Okay, so in building this, we think of us putting a standard basis element in, something like this, 1s and 0s everywhere else, and the output's going to give us something like this, which we could fill in for a column. We're going to focus on what happens at the top, thinking top row, if this element is associated at the top of the vector, on the top of the matrix here. So notice that everything outside where these circled entries are is going to contribute. So if it's a standard basis vector with a 1 here, it's going to contribute a 0 to the top. But if we're actually inside these circles, we contribute something else. Like if we had a 1 here, the solution would look something like this: 1, 1, 1, and a -1. negative 1 contribution. If we were right here, for instance, we get negative 1, positive, we'd have a positive 1 contribution to the top. So see how it alternates up. And if we were right here, we'd have a negative 1 contribution to the top. So it alternates up. That is because this part right here, it has a power set structure. You notice a power set on a collection of 3 different things. Okay, so, and that's where we're going to get that, and we have this alternating thing of contributions up to the top. So this power set structure, well, here's a little depiction from power set turn upside down. What I've done from the original is you take 60 divided by each one of these guys in turn, and you're going to get a number. Like 60 divided by 30, for instance, is going to be 2. 60 divided by 10 is going to be 6, which is like 2 times 3. And if we take a look over here, see that 2, 3, but I'm writing with commas as a list with these factors. Notice that when we're in this top power set structure right here, notice it looks like a power set. But out here, it does not. It looks like multi-sets. I mean, we have repeated things. All right. So really what we need to be able to do is pick out what's in the top Poset part and then contribute either 0 to the top or a 1 or a negative 1. And the arithmetic Mobius function is just the thing that will do that for us. Okay, so after we go ahead and we say like 60 divided by the number like we were doing, then we throw that guy into this Mobius mu function to see what the contribution is going to be at the top. So if we have a square factor, that's like having a repeat in our factors after we do this. So we're going to contribute a 0 to the top. Otherwise, it's going to alternate depending on how far below we are. And that just has to do with the distinct prime factors that we have, because we're taking those are becoming our sets in our top power set structure. So that's really what the Mobius mu function is. And it gives us a way of computing top summands. Or top nodes, if you will, if we have something that represents sums. So here's an example of kind of what we would do, what we'd get out. Okay, yeah, so in our calculation, for instance, if our sums ended up being just the factors themselves, okay, and we wanted to figure out what the top node would be in the solution to that, we'd run this through, right? This would be the top row of our matrix, and multiply that out. That's kind of how we would do that in that particular case. Okay, now what if we wanted to compute something like number of primitive bit strings, binary bit strings, so strings of 1s and 0s, and let's suppose we have strings of length 36, and we want to know how many primitive bit strings are. What does primitive mean? That means it's not made up of a repeating pattern of any kind. So it wouldn't have come from a bit string of a smaller size. So that it evenly divides this divides that one. So for instance, you think factors of 36, 18, 12, 6, 4, you have this whole thing right here. And so really in computing what's new, you think, okay, 2 to the 36 is how many total binary bit strings of length 36 are. This is how many total of 18, 12, 6, and so forth. So, but these totals, what we add on, must be something that doesn't come from any one of them, which means it's primitive. It doesn't come from a repeating pattern of what's below it. So really, we can use the Mobius mu function to compute something like this, like what is the top solution, like right here. So what we do is we can pick out the top power set structure, which we've done right here, and okay, the top, and this is for 36. So really, I mean, these are the things that we're plugging. This is like what we're plugging into the Mobius matrix. But notice I'm only working with these 4 elements. These other guys are outside. We're gonna have zeros attached to it in there, so I kind of ignore that in the calculation. But really, this comes from the divisor Poset structure with 36 at the top, and going down from there. And notice I've taken 36 divided by, so 36 divided by 36 at the top, and then down would be 18 divided by 12, 6. Compute the Mobius mu function of those guys, get plus ones, minus ones, minus ones, plus ones. All right, and just attach it to that, and there we have it right here. This calculation right here would compute how many primitive binary bit strings there are of length 36. And that's a description of the arithmetic Mobius function from a Poset perspective. Thanks for watching.